I will begin with a word of prayer. Let's get it up here. Heavenly Father, we thank you for this day. Again, I thank you for your many blessings, and I just pray that you be with us, class. Help us to glorify what we do and understand a little bit more about your creation together, Lord. In your name I pray, Lord Jesus. Amen. All right, so are there any questions about anything before I get started? All right, I guess not. So then, I want to talk to you guys a little bit about the Cauchy Euler problem. And it's also sometimes called the equidimensional problem. And it concerns how do you solve something of the form, let's say an, I'll use x to the n, d to the n, plus an minus 1, x to the n minus 1, d to the n minus 1, plus dot dot dot, plus let's say x a, a1 xd plus a sub 0, all of that acting on y equals to 0. So this is the Cauchy Euler problem. So like n equals 2 would just look like this. You've got like a x squared d squared y dx squared plus like bx dy dx plus c times y equals to 0. This is the n equals to 2 Cauchy Euler. All right. Now, goodness, I'm trying to remember. I took differential equations when I transferred to NC State. I had like 2-year degree in electronics from a community college. So I joined the engineering program. So I was in this transfer differential equations class, and I don't think we ever covered the Cauchy Euler problem until the final exam. At which point he had a problem on it, which was like, wait, what? But it was not unreasonable, because the question on the final simply said, if you let y equals x to the power r be a solution, what condition do you need on r for it to solve it? Right. So I'll start with this. I'll start with the n equals 2 case because it's less formidable. We'll start over here. So if we make a guess that the solution has the form y equals x to the power big R, let's say, because my little r's are hideous. So big R. What happens when you differentiate this thing? You get r x to the r minus 1. What happens when you differentiate 2 times? You get y prime prime r minus 1 times r times x to the power r minus 2, right? So I'm just doing power rule. Nothing too fancy going on here. And if you plug the guess back into the differential equation, what happens? So take these, plug them back in up there. What does that give us? Gives us something cool happens, right? So like we have a x squared r times r minus 1 x to the r minus 2 plus b x r x to the r minus 1 plus c x to the r. Right? We'd like that to be equal to 0, right? Do you notice what happens here? So by the way, the reason it's called equidimensional is because as you look at the differential equation, you have the dimensionality of the x squared, which is like a unit of length, right? But then you have the derivative, which is like dividing by length. So it's equidimensional because you have power 2 dimension, power minus 2, power 1, power minus 1. So it's like there's like this matching of the dimensions, if you will, of length in the construction of the differential equation. Yeah?
You can factor out x to
Oh, okay, yeah, x to the r. And what you got? You got a r times r minus 1 plus br plus c all times, like you just told me, x to the power r. Well, this isn't too bad. It looks like all we need to do is solve that characteristic equation, right? So in this case, oh man, yowzers. Characteristic equation here, we need, a r times r minus 1 plus br plus c equals to 0. This is the characteristic equation for the Cauchy Euler problem in the n equals 2 case, right? And if we can solve that, then whatever we find as solutions, that should give us powers of x which solve the problem, right? Can we solve that? Yeah.
No, I'm sorry, I'm not answering your question. I just have a quick question. Why can you, when you factor out the x to the r, can you also get rid of the x squared that the a is attached to?
Oh, because I'm multiplying this times that. So x to the squared times x to the r minus 2 is x to the r.
Okay, thank you.
And likewise, like same thing over here, right? This times that. When I do laws of exponents, I get x to the r. Now, the larger point here is we need this solution to work for all x, right?
Yeah.
So that's the reason the coefficient has to be 0, independent of x, yeah? And something funny goes on with this differential equation at 0, right? So this one's very different than the constant coefficient problems we've been working. Constant coefficient problems, they have domains. The natural domain of definition for the differential equation is like the entire real line. This one, funny stuff happens at 0. So the solutions are either going to be good for positive x or for negative x, but we can't cross 0 into the solution for this one. 0 is what's called a singular point. Technically, it's a regular singular point, as we'll discuss later. Maybe. But hey, my question is, can we solve this boxed equation? The answer to my question is yes, categorically, always. This is a quadratic equation in R. It cannot escape your clutches, right? You know how to complete the square. You own these, right? So n equals 2, we're good. And we'll do examples. But how about this? Well, it's the same thing, right? It's just, instead of, you let y equals x to the r, and then what you're going to get is an, r times r minus 1 times r minus 2, and so forth and so on. How many times? How many factors did I get over here? I got one less. See, I had a y prime prime. I went all the way down to r minus 1. So it goes all the way down to r minus parentheses n minus 1. That's how far the leading term goes. And then an. And then I'll spare you the next term until we get all the way down to like a2 r times r minus 1 plus a1 times r plus a naught. And you know what factors out of that? X to the power r equals to 0. It's the same exact calculation I did for n equals to 2. It's just you've got more differentiations and hence more uglification of your quote-unquote characteristic polynomial. So then this is a nth order polynomial in R. It has n solutions, possibly repeated, possibly complex. So both of those, the repeats and the complex, it's going to take us a minute to wrap our mind around that and see what those solutions look like. But actually the story is going to pretty much remain the same as it did before. in terms of the repeat. Well, okay, now that's not quite true. Before we saw that when there was a repeated solution, we just ended up multiplying the exponential by what? Yep.
Is there a reason there's an an before and after that first term?
Oh, that's probably a typo. Assume that's a typo. When I get back up here, when I can read the board again, it only comes into focus for me when I get about here. Oh yeah. You don't need two. One's enough. Thank you. Cool. Excellent. So let's look at some specific examples in the n equals 2 case, because that's mostly what I'm interested in here. Example 1. I don't know. How about x squared y prime prime equals to 0? All right. So I write down my characteristic equation. This one is r times r minus 1 equals to 0, which tells me I've either got r equals to 0 or r equals to 1. Therefore, my solution is c1 x to the 0 plus c2 x to the power 1. In other words, y is equal to c1 plus c2x, which is kind of unsurprising. And all that stuff I was just telling you about, oh, the domain of definition, it fails at 0. You can't really see that in this example at all, right? It's really hard to tell the difference between this example and simply y prime prime equal to 0. All right. They are technically different examples, as this differential equation is not actually, in some sense, it's singular at 0, so things are a little wonky there, although I'm not sure how true that is for this example. Let me go on and make something uglier. Any questions? Do you see I'm just following the method? And the general theory is still the same. This is an n equals 2 problem. We're looking for two linearly independent solutions. All right? And that's all we need to find. Yeah?
Where does this find functional application?
Oh, if you look at Laplace's equation in polar coordinates, you get a Cauchy Euler equation for the radial part of the solution. So for example, if you want to find like the voltage inside a circular disk, you use it there. If you wanted to solve like vibrations of a drum, again, polar coordinates.
Mostly for polar coordinates.
Yeah. It just turns out that like when you do separation of variables on the Laplacian, on the Laplacian, you end up with a Cauchy Euler problem in the radial solution. There are other things, I'm sure, but that's what comes to mind for me right off. Example 2, what if we had like, how about x squared y prime prime plus 2x y prime? Then the characteristic equal to 0. Characteristic equation, r times r minus 1 plus 2r equals to 0. All right, so this gives me r squared plus r equals to 0, right? This is kind of the same example almost, but it's actually really different, right? Because here we've got characteristic values 0 and minus 1, right? And this solution I'm about to write down is something we would not have seen before. This is y is equal to c1 plus c2 x to the minus 1, which of course I would usually write c1 plus c2 over x, right? Now maybe you can start to appreciate why I'm saying 0 is special. This solution's not defined at 0. That's not an accident. That's usually characteristic of these solutions. Okay, how about example 3? What if we have x squared y prime prime plus 5, oh, that's not what I want. I'm sorry, give me a second here, I'm thinking. Plus xy prime plus 5y equals to 0. let's take a stab at that one. See what happens to us. I'm not sure how to classify that noise. Let's see here. A soft stab. It's ripped from the headlines. Let's see here. That's maybe too dark for today. Let's see here. Oh, goodness. Do I need to edit this video? It's on the bubble. It's on the bubble. Unfortunately, I no longer have video editing software ever since my son redid my Windows after a Bluetooth episode about 2 weeks ago, 3 weeks ago. I don't know what happened, but he just redid Windows, and in the process, I lost my LaTeX editor, my all kinds of stuff. And among those is my video editor. So I try to make it good the first pass. So there's a certain amount of politically incorrect comments I must forbid. Anyway, hey, but being politically correct is part of the founders' vision for this place, right? So it should be okay. Okay, so characteristic equation. We get r minus 1 plus r plus 5 equals to 0, which gives me r squared. Oh man. Okay, fine, it is. Can I not put 5 here? If you guys don't mind, this is a freedom I have that you don't. I'm going to change this 5 to a 4. There we go. And now we will have r squared plus 4 equals to 0, which tells me that r is equal to plus or minus 2i. Of course, this can happen. The question is, what do we do with it? All right? So really the question is, what on earth do you mean by, x to a, well, let's just talk about this. If I have x to the alpha plus I beta, I'm going to make that mean x to the alpha times the cosine of beta natural log of x plus I times the sine of beta natural log of x. This is a definition for us. And I'm assuming x is positive for this current definition. If you had x as negative, you need to replace the x with absolute value x, okay? Now you might wonder where on earth this formula came from. Let me play around with x to the 2i for a second. All right, so x to the 2i, right? How can I rewrite that in terms of exponentials and logs if you believe in that kind of thing? Well, I could trade this for exponential of the natural log of x to the 2i. Now, don't tell Dr. Majeric, because if you tell him what I just wrote, he's going to say, you can't do that. That's in formal violation of the rules and definition of the complex logarithm as we talk about in Math 331, and that would be true. But it won't harm us here because you guys aren't taking that course at the moment. And by the time you take it, you'll have forgotten this, so it's okay. But really, okay, let me explain myself. What I'm doing right now is a formal heuristic. I'm not deriving. This is a formal heuristic. In other words, it's something I tell myself to remember a formula. So if that's true, like you'd like that to be true, power law for logs, right? Still working for complex. Well, we already defined the exponential of e to, remember e to the I theta, other lecture? E to the I theta, thank you, Euler. Cosine theta plus I sine theta. That is, I mean, good grief, we've known about that since the mid 18th century. It ought to be in high school by now. Come on. You know?
Sure.
Yeah. Let me live in my delusions, please. All right, let's see here. So this is the cosine of 2 log x plus I times the sine of 2 log x. Just thinking of, I'm thinking of theta equals to 2 log x here in Euler's formula. Okay, so that's why I put cosine beta log x plus I sine beta log x here. Does that make sense? I mean, it's part of a program here of notation. And the x to the alpha, well, that just belongs there because if you got a real part, it should still just be the regular old power function. Okay? Anyway, this short tour of what on earth do we mean by what on earth do we mean by, you know, x to a complex power? Well, this is what we mean. The definition's right there. And so in light of that definition, my solution is y is c1 cosine of 2 log x plus c2 sine of 2 log x. There you go. That's the general solution to this Cauchy Euler problem. We want the general real solution. So I would not be happy if you guys wrote for me the solution. Let me write it down and then cross it out to emphasize what I'm trying to say here. This right here is for another course. This does not belong in your current course because this boxed expression that I will soon make red, the thing in the red box, soon to be crossed out, is no allowed in here because this is not a complex variables course. This is a real differential equations course. We want real solutions. That's not a real solution. Yeah.
Is there a reason there's not an I present in the...
Yes, we want a real solution. So remember the structure that we looked at? If you have a real differential equation and you find a complex solution of it, the real and the imaginary part are separately solutions to the differential equation. So, like, you know, the real part and the imaginary part, they're separately solving that differential equation. Now, I don't know about you, but I'm willing to believe myself that it works. Because the process of actually checking that this is a solution to that would take a minute. You see, we'd have to differentiate this thing twice, multiply by x squared, then add x times the first derivative, and then finally add 4 times itself. Somehow that stuff all cancels out to give 0. It's really quite amazing, honestly. I don't think I would have thought of that outside of this technology, let's say. Yeah? Yeah.
Now, when we go to do this, we're just going to use Euler's formula there.
This is a definition. You're free to use it, right?
But then we'll have all the solutions, and then we just cross out the imaginary ones.
You just pick off.
Yeah.
I mean.
But we go through that whole same process.
Right. What's that? It's not I, but Christ who lives.
It's an imaginary gift. I'm sorry, guys. Shouldn't have.
There's no I in team, but there's 2 in winning.
Yeah.
There you go. I'm not sure where that's from. My children somewhere. Let's see here. All right, let's see if we can find another one of these characters. All right, example 4. Suppose we were up against x squared, y prime prime, I'm thinking plus 3xy prime minus y equals to 0. Can we solve this one? So the opening move here. Where is he? Is the president here? No. Oh man. I just made an opening move. There's no one here to hear it. All right, anyway, so r times r minus 1 plus 3r minus 1 equal to 0. Characteristic equation. Hooray! Factor we get r squared plus 2r minus 1 equals to 0, also known as r minus 1 squared equal to 0. Or not. Wait a minute. Aw, man. Well, let's take my... All right, I'm fine. I'll take my medicine. This is r plus 1 squared minus 2, is it not? Which means that this is r plus 1 minus, is the square root of a 2? Times r plus 1 plus the square root of 2 equals to 0. It's fine. We should deal with an ugly one. So here it is. C1 e, listen to me. No, x to the minus 1 plus root 2 plus c2 x to the minus 1 minus root 2. There you go. Solved. That's not what I wanted to happen. I wanted it to be uglier. In a different way. Let me see if I can make up another problem. I was trying to get it to make. I was trying to get us a, repeated root, right? So example 5. Maybe I'll. Can you guys help? How would I fix that to make it repeated? What would I do? What do I do? Same problem, but do what? This isn't like making up problems. Isn't usually your problem, right? But if you want this to become a repeated root, I just need this to be a what? A plus 1. So I should have just added y to make my example what I wanted. All right. Find the characteristic equation. What do you get? We should get r squared plus 2r plus 1. That was a hiccup. I know that when I hear it. Let's see here. So r times r minus 1 plus 3r plus 1 equals to 0, which of course is giving me r squared plus 2r plus 1 equal to 0, also known as r plus 1 squared equals to 0. Aha! So we have r equals to minus 1 twice, right? What do we do with that? I mean, part of it's easy enough. My y1 is, x to the minus 1. If you like, it's 1 over x. But what about the other one? What do you do when there's a repeated characteristic value? Where's the other solution look like? So I want to show you a kind of formal calculation to understand. There's a lot of different ways to look at this, but here's a kind of fun one. So let's go back to the constant coefficient case, right? Remember we had e to the lambda t versus lambda, versus t e to the lambda t, right? How do you get from here over to here? What do you do? What calculus will take you from there to there? We already know those work from our work on the lemmas, right? Can we look at this a different way? Let me see. What's that?
If you integrate with respect to lambda.
Integrate with respect to lambda. Right idea, but instead of integrate, differentiate.
Oh, sorry, yes, right.
That's what you meant. So the reason, if we take partial lambda of e to the lambda t, holding t constant, that gives us e to the lambda t, partial lambda t, which is, of course, t e to the lambda t. Right? So if this is not just a quirk of the constant coefficient case, but in fact part of a general trend, it is, we can derive from the x to the r solution what we need to do in the repeated case. So how's that go? partial r. That's what? It's not r times x to the r minus 1, is it? Yep.
I'm confused about what R is. Because I recognize this from when we use D like this, and D is an operator.
Yeah.
So what is R?
R is a temporary, it's a scalar variable. It's the coefficient. We're guessing every one of these, we're just putting y equals x to the r. And here r is, complex, possibly complex scalar. So it's just the guess that we started class with, which I first encountered on my final in this course. But anyway, the engineers complained about that a fair amount after class. But I love Dr. Fauntleroy. He was a great professor. They would complain about something, blah 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 blah. He'd turn around at him. He'd just turn around. He was always wearing drawstring pants. His wardrobe was ripped from the 70s. He was still wearing 70s leisure wear. This is the late 90s. And he sounds exactly like, his voice is Morgan Freeman. He sounds exactly like that. And he just oozes coolness, this guy. And he'd just look at them and he'd be like, it's just algebra, man. It's just algebra. And then he'd turn around and keep working. Never really answered their question. It was beautiful. It was like, oh my goodness. Oh, that was a fun class. Anyway, so here, because we're differentiating the exponent, this is an exponential function. So the rule here is the log of the base, which in this case is x. So this is what happens there. So in light of that, my solution actually is c1 divided by x, good grief, c1 x to the minus 1 plus c2 natural log of x times x to the minus 1. Or if you prefer, and I kind of do, this is c1 plus c2 log x all divided by x. You could write it like that if you like. That's the general solution to this problem. What do you do if you have a three-peated solution? Like, don't make me write down the differential equation because it's a pain. But if you could imagine something here, third order, all right? And it gave you r equals to 7, thrice. Then the solution would be like c1 x to the 7th plus c2 log of x times x to the 7th plus c3 log of x squared times x to the 7th. That's how that goes. Just in the constant coefficient case, you multiply by t each time. If you had a three-peat, you multiply by t, then you multiply by t squared in order to create the solution set. So that's how this works here. Your question, though, about operators is a good question, and that's actually a really good question to ask, which is, can you look at this problem in terms of operators, and how does that work? That's a harder question. Because the trouble here is these operators don't commute. You see, well, let me get my projector out here. I have things to show you, I suppose. That's pretty much it for how to solve Cauchy Euler problems. So you can tack on this. Well, let me show you variation parameters. Come on, work. Let's see here. I guess there's a couple of other points I should make here while we're on this part of the material. I mean, this way I just derived the repeated solution. It's kind of hocus pocus, you know? I mean, it worked, right? But it does beg the question, is that really theoretically the way you should do it? And so like this section right here gives you a more serious answer to that question. So this is like the reduction of order formulas. Basically, this shows how to take an nth order problem and make a velocity substitution, and then reduce the order by 1, and just keep doing that. And in so doing, you can change an nth order into a first order after a bunch of substitutions. You integrate the first order, that gets you back to the second order, and you just kind of integrate your way back up. That's another way to solve these. Oh, but it comes at the cost of these rather ugly, in my opinion, reduction of order formulas. However, when you apply this idea to the order 2 case, something kind of cool happens. If we, so this is the so-called second linearly independent formula. So here's the context. Suppose we've got a second order differential equation of this form. Suppose we have one solution, all right? The question is, how do we get another? All right, that's exactly the question I answered here with the hocus pocus of partial lambda, right? What's another way? Well, if you have one solution, you can let your second potential solution, y2, be v times y1, where v is an unknown parameter. You plug that into the differential equation, all right? I mean, you want y2 to be a solution, obviously. So when you plug it in, it gives you this business, but you already know that y1's a solution, so that's 0, which makes this simplify to that. And then we make a substitution of a velocity substitution, z equals v prime, which gives z prime is v prime prime, which then gives you this first order differential equation in z, like I was talking about. This is reduction of order. And it just so happens to give you this linear differential equation in z that involves the solution that you know, its derivative, and the coefficient. No, by the way, the a, b, and c here could be, well, they are functions, all right? They could be functions. So that's why we have words. No, enough words. So we solve that. That's by the integrating factor method, but that's the integrating factor. Lo and behold, we have z is equal to this, but z is dv dx, which gives us that. And then lo and behold, there's a formula. So y2, you take y1 times the integral of the exponential of this jazz for your differential equation, and that will produce a second linearly independent solution from your first. All right? And you can do that. For example, here's back the constant coefficient problem, my linearly independent first solution, e to the x. Suppose I've got a repeat. This is like lambda minus 1 squared, right? So if I plug this formula up here into that case, I got to do this integral, this, it gives us x e to the x. This derives the x from this argument, all right? We get x e to the x from this second linearly independent formula. And if you do the same thing, oh, come on, did I not do it for the Cauchy Euler problem here? It must be in my Cauchy Euler section. Let's go on. Let's skip past this operation. So here's the Cauchy Euler section. We've got some examples here. Here it is. So if we use the second linearly independent solution formula in the context of the Cauchy Euler problem, in this particular one, which is r equals to 2 repeated, we get this business, which gives me that, which integrates to, well, that's it. This is an x cubed after you do the algebra, and then x cubed over x to the 4th gives me 1 over x, which gives us, x squared log x, which is what we already knew from our hocus pocus argument. Because we have r equals 2 repeated, so we've got x squared my first solution, log x times x squared for my second solution. There's the general solution. So, yeah. So, if you'd like, I could spend a half hour of class like carefully deriving the second linearly independent solution formula. But in the past when I've done that, it's been a possible test question. So you don't want me to do that. You're content to know that there is a way to derive the second repeated solution. All right, that's it. Now, back to your operator question. How can we look at this in terms of operators? So basically, here's the deal. It is possible to take the Cauchy Euler problem and rewrite it as a polynomial in the operator x times the differentiation operator. You could always look at it as a bunch of x times the differentiation operator acting one after the other. Like, these are what these calculations show. If I take xd minus a times xd minus b and you work it out, you get this. So the way these multiply, it's not just polynomial multiplication, right? The differentiation operator, very, very forgiving. If I have d minus 3 times d plus 2, we just multiply them out. We don't even think about it. But this operator doesn't commute. Like xd doesn't, oh, I'm sorry, what am I saying? No, I'm wrong, I'm an idiot. Look, actually, this is the opposite of what I'm saying. This is just what you expect. If I multiply this times that, I have, oh, rats. I'm sorry, I've been away from this calculus for a bit. I'm trying to remember how to say this better. Let me go on here. I hope I have a calculation here I can show you.
How do you pronounce it? Cauchy Euler?
Cauchy Euler.
Cauchy Euler.
Oh, here, this is what I was looking for. The x squared d squared operator is actually the same operator as xd operating twice, one after the other, minus the xd operator. That's what this calculation shows. See, if we take xd times xd acting on f, that's xd xdf, which is xd xf prime, which when I differentiate product rule gives me x times f prime, because the derivative of x is 1. And then this one, x times x is x squared, and then f prime prime, like that. But that is x times d plus x squared d squared acting on f. And since this holds for an arbitrary function f, that shows you that xd squared, this xd squared is equal to xd plus x squared d squared, which if I solve for x squared d squared gives me that.
So you're saying that differentiation operator is not as flexible as you were saying initially?
I'm saying that the mess of the characteristic equation is the same mess as this problem. Like, it's the same mess. Here's how the cube works. The point is there are formulas, and you can convert this to a polynomial in xd. Now, once you have everything written in terms of a polynomial of xd, then you can treat those like polynomials. Those commute, and you can factor it just like you do the constant coefficient problem. So, yeah, I'm trying to find somewhere I should have a. Give me a second here. Let me look for something. Oh, don't do that, computer. Computer, behave. All right. So basically, based on the question you're asking, I wrote a paper with my brother called The Generalized Method of Undetermined Coefficients. And we published it 2022, I guess. And in this paper, we look at, if I can get to it, basically how to solve. Let me try if I can find an example here. If I can just get to the examples, it'd probably be good. Rats, I went past the examples. So like the main result is if we have, oh no, you know, this is part of that Windows thing I was talking about. Somehow the ad block has come back to my idiot Chrome. I gotta get rid of it again. YouTube keeps threatening to like cancel my account or something, which would be be bad. I know, I'm trying. Thank you. Do you have another suggestion of ad blockers, though? What's the?
You block origin light.
You block
origin.
You block origin? Okay, thank you. I first learned of ad blockers from students, so every once in a while I have to ask you guys what's the current thing, you know. Anyway, so this is the theorem. If I have g dt, so like g equals to 1 is the constant coefficient problem. G equals to t is the Cauchy Euler problem. But we worked it out for an arbitrary function g. And it turns out that you can solve any polynomial in S for your operator. I can find a solution set, y1 through yn. And the solution set is formed, this is one, like, okay. Come on. I don't talk about this too much, so here's the solution set. So if I have g dt, if I have something like this, the fundamental solution set is e to the alpha h cosine beta h, e to the alpha h sine beta h, and then h to the k minus 1. Here h is what we call the multiplicative function. H is actually the integral of dt over g. So in the case that you've got the constant coefficient problem, the h is just t. In the case that you've got the Cauchy Euler problem, the h is natural log of t. But this works for anything else as well. So actually the stuff we do in this course generalizes to a whole host of other problems that you will not find in differential equations book, and no one cares about, except the like couple hundred people who've downloaded this paper, I guess. But it's a good thing to, if you ever want to make like a math camp and create problems that they can't solve with like ChatGPT, this probably is the way to do it. Until ChatGPT has another like improvement or two. I mean, I fully expect that the time is soon coming that ChatGPT starts doing, maybe not ChatGPT, but one of these generative AIs will start doing mathematics that's above the level of mathematicians. I fully expect this. Because it can think about more than we can at once, you know. There's no way I can take in the work of 1,000 different mathematicians, the totality of decades of their work, but maybe 10th generation generative AI can. So in as much as the work they've been doing hasn't been groupthink, it's actually been quantitative, objective research, which is what mathematicians do. That could be actually very interesting. I don't think it really will help much for other fields. But anyway, that is my arrogance. But I think it's well-founded. Not me so much. But okay, so I wanted to give you guys a surprise tech mission. And it would be good. I do need it back Friday. I do not want this electronically. This must be turned to me physically. No emailing this. Understood? Okay, so if you're not here and you're watching this video, you need to come and get this or print it out. I don't think this will take long, but I do need to start a class Friday, so thanks guys.